The warm-up problem for today says a 0.071 kilogram paper cup falls from a 0.78 meter high table. If there is no air resistance, what is the change in KE of the paper cup? And then what causes this change in kinetic energy? So that's our warm-up. We're going to go over that. And then, as I said, we'll be taking notes. You'll have a problem set due tonight, and then your RA is due tomorrow. So, if we're addressing the problem that we just read, if we're trying to do this calculation, we're trying to find change in kinetic energy. Again, anytime you're doing a calculation, label your givens. We know the mass, 0.071 kilograms. We know the initial velocity is 0 because it says that it is falling. So this is similar to our free fall problems that we did previously this semester. But if it says that it falls, then it is implied that it is falling from rest because it doesn't say that it was thrown. Okay, so my initial velocity is going to be 0. The displacement, or the amount of the change in position that is covered, is a downward direction in 0.78 meters. So the displacement is negative 0.78 meters because it's falling down, and we're going to call down the negative direction. So its displacement will be below where it started. And then the acceleration in this problem is also downward because it's acceleration due to gravity. Again, we're treating it like a free fall problem because it is. So we have mass, we have initial velocity, we have our displacement, and we have acceleration. And we're trying to figure out change in kinetic energy. And we've done change in kinetic energy problems a few times. When we did them previously, we tried to figure out what the initial velocity and final velocities were so that we could figure out what the initial kinetic energy and final kinetic energy was. And that way we could find the change by subtraction. And we can still do it that way. That way is still a good way to solve it. You do have another option, though. In your RA, you saw that, or should have seen, that the change in kinetic energy of Wally was equal to the work done on him, or at least it should be pretty close. You're doing a lab, your data collection might not be perfect, but hopefully you saw that. If you didn't see that and your numbers were very different, here's your hint that you need to go back and look at something, because something is wrong if they are very, very different. Okay, they should be the same. We're going to talk about that today. So the other way to solve for this is by solving for work, because work should be equal to the change in kinetic energy, and we have an equation for work, which is force times displacement. Now, I don't have a force, but I do have a mass and an acceleration, and so that would be another valid way to approach this problem. Okay, so you've got a couple methods. I'm going to go ahead and do it the way we did it previously, which is find the final velocity because I already know the initial. And then once I have my two velocities, I can use those to find my change in kinetic energy. So again, I'm going to use some kinematic equations, specifically this one. Vf squared equals Vi squared plus 2 times A times delta x. And I chose this equation because of the information that I already know. I know Vi, I know delta x, and I know A, and I'm looking for Vf. So when I substitute in, I have this, and I can use it to solve for Vf, and I don't even have to rearrange it. I have 0 squared plus 2 times negative 9.8 times negative 0.78. Again, 0 squared is going to be 0, and I'm adding it, so I'm really not doing anything with it. I just need to multiply those other three terms. When you multiply those, you get this, 15.288. And again, that is equal to Vf squared. So you still need to take the square root of both sides. And when you take the square root of a number, okay, the square root of 15.288 is plus or minus 3.91. You guys remember that from math? When you take the square root of 9, it's plus or minus 3. Okay, in this case, you need to remember that, oh wait, it's going down, and you need to pick the negative one, okay, because it'll be plus or minus, but you want the negative one because it's falling. So my final velocity is negative 3.91 meters per second. Again, that's not my final answer because we haven't answered the question. I still need to get change in kinetic energy. So we're going to use that final velocity now to find our final kinetic energy. Our initial kinetic energy is 0 because it started from rest. my final kinetic energy has to be calculated. Now, the fact that I needed that negative sign in front of it won't matter here because I'm about to square it. Okay, so it's going to go away. So if you forgot the negative sign here, it wouldn't ultimately make your answer incorrect at the end of this one, but sometimes it could, so be careful with your signs. All right, so 1/2 times 0.071 times 3.91 squared, and that's going to give you this. My final kinetic energy is 0.543 joules, and so my change in kinetic energy, obviously if I started with 0 and now I have this much, it's a change of positive 0.543 joules. I rounded it a little bit more than that, 0.54 joules, and you can go ahead and enter that in your warm-up in the Google form. So my change in kinetic energy is positive 0.54 joules. All right, so again, we've done this type of problem many times now. I just wanted to go over it again. But I mentioned there was another method. If you wanted to do it that way, you could, because that's what's going to be the topic of our notes today, is the fact that my change in kinetic energy is going to be equal to the work being done. Okay, so what causes this 0.54 joule change in kinetic energy? Why does my cup have more kinetic energy than it started with? Why does it gain kinetic energy? What's it doing? Yes, it is falling, but what is it doing? Speeding up, right? It's getting faster. And so I have a change in kinetic energy because it's getting faster. And the reason it's getting faster is because gravity does work on the cup. Okay, I've already mentioned this. I could have solved this by finding work. Okay, the amount of work done by gravity would also be 0.54 joules. If you have a change in kinetic energy, it's because there was a force doing work. In this case, gravity doing work on the cup. It added energy to the system, causing the cup to speed up or to gain kinetic energy. All right, and that brings us to our notes, work energy theorem. Okay, so the work energy theorem states that the net work done by the sum of all the forces acting on a system equals the change in kinetic energy of the system. I mentioned that a second ago with the warm-up. We could have found work because the work done equals the change in kinetic energy of the system. You should have seen that in your lab. If you, again, have data that doesn't show that, something is wrong. Some number somewhere is wrong. Okay, so you need to double check that. Again, the net work, since this refers to net work being done by all forces, as a reminder, net work is the sum of the forces, the sum of the works acting on the system, which is going to be due to the net force as well. But it's your positive work plus your negative work. And of course, if you have both, it will end up being subtraction because you're really subtracting that negative work. If you have work energy theorem, you can write it in either of these two ways. You can say that the initial energy of your system plus any net work on the system, and that could be a positive or a negative value for net work, will give you your final energy because this represents the change. Or you could write it this way, net work equals change in energy. And again, change in energy would be E sub F minus E sub I. It's the same thing rearranged. But that's your work energy theorem, is that the change in energy of your system is equal to the net work acting on the system. All right, so again, back to our warm-up. We already found this. What is the change in energy? If I take a look at the equation I just gave you for the work energy theorem, I can plug in and solve for the net work. My initial energy was 0. My final energy was 0.54. And so if I wanted to find the net work, I could simply set up to solve for W net, which in this case is going to be equal to 0.54. It's the same thing. Again, that's what the work energy theorem states, is that the change in kinetic energy of your system will equal the net work being done. You can prove it mathematically as well, as we just did. All right, so again, as a reminder, work can be positive or negative. We've already talked about this. You don't necessarily have to write it down again if you already have it. But work can be done to add energy into a system. So the example I have here is a desk is initially at rest before it is pushed for 5 meters with 60 newtons of force, giving it a speed of 3 meters per second. So again, that would be an example where we have positive work being done on the desk. And the reason that it's positive work is because the force is in the same direction as the displacement. Or you can think of it like this way, The work is positive because it adds energy to the system. It was at rest and now it's moving, and so you have kinetic energy that you didn't have to begin with. Okay, and so the energy of the desk would come from the net work being done. You can write an energy transfer equation. You can say that the total initial energy, which was 0 because the desk was at rest, plus the work being done, in this case by the force of 60 newtons for 5 meters, would equal the final kinetic energy of the system. Okay, and so you can actually use an equation like this, an energy transfer equation, to help you solve for maybe what the mass of the desk was, okay, or something like that, depending on the information you're given. But again, that would be the energy transfer equation because the initial energy was 0 and the final energy is kinetic. Okay, so you can see that equation there. Again, work could also be negative because it can remove energy from the system. The example I have here is a 0.5 kilogram ball initially moving at 4 meters per second, rolls to a stop after 7 meters due to friction. In this example, the ball had kinetic energy and lost it because it went from motion to stationary. And so that would be an example of negative work because it loses kinetic energy. It's also negative work because of the definition for work. The force of friction is opposite the direction of the motion of the ball, and so it's also opposite the direction of the ball's displacement. And any time your force and displacement are opposite, you get negative work. So again, whichever way helps you remember that. But the kinetic energy of the ball in this case was dissipated due to negative work done by friction. And dissipated just means lost from the system. It goes into the surroundings. Friction specifically tends to generate heat, which is not a really useful form of energy. It's not mechanical energy, but it is still energy. Okay, but if you rub your hands together, again, you can generate heat by friction that way as well. So it generates heat, but that means that it's dissipated from the system. It's no longer mechanical energy. It's no longer energy of motion, kinetic energy. Energy transfer equation in this case would be my initial energy, which would be kinetic, plus the net work done equals 0 because it doesn't have any work at the end. There is no final energy at the end. Or you could also just say that the kinetic energy is all dissipated energy, which means it would be equal to dissipated energy. We'll talk more about that one later, but this one is just in the same format as our work energy theorem. Initial energy, kinetic, plus net work equals final energy, which in this case is 0. All right, so what is dissipated energy? I mentioned it on the previous slide. Dissipated energy is energy that is lost from the system. So in an open system, sometimes the work being done causes energy to be lost from the system so that it's no longer available to do work. The ball on the last slide loses kinetic energy due to friction, or if you had a sled moving across the ground, it could lose kinetic energy due to friction. The energy still exists, it generates heat, it's just no longer useful. The amount of work done by friction will be equal to the amount of energy dissipated from the system. So in the case of a force that is causing negative work, like friction, the amount of energy lost will be equal to the work done. And again, that's still work energy theorem. Change in energy equals work. Okay, so the amount lost will equal the work being done. All right, let's try this example problem. If you want to copy this one down, it would be a good one to have in your notes. This is on slide 63 if you'd like to follow along. It says a custodian pushed a 25 kilogram desk from rest along a horizontal surface until it reached a speed of 3.5 meters per second. What is the work done on the desk? Again, label your givens. We know the mass of the desk. We know that it starts at rest. We know that it reaches a final velocity of 3.5 meters per second. Okay, and that's the information that they gave us, and they're asking us for work. Okay, again, work is force times displacement, but if I look at this, I don't happen to have those things. Okay, I don't have force or displacement here. Work is also change in kinetic energy. I do have the information for that. So sometimes it might ask you for work and you don't have the information to plug into the work equation, but if you remember that work is equal to change in kinetic energy, and if you can find that instead, you'll be finding work. It's kind of similar to the impulse momentum theorem that we had last unit, where they might have asked for impulse, but if you had the information to find change in momentum, it was the same thing. It's the same idea. If they ask for work and you don't have the information for that, but you do have the information for change in kinetic energy, it's the same thing. Find it instead. Okay, so the equation, we're going to write our own. Okay, we're going to start with our work energy theorem equation, which is initial energy plus net work equals final energy. That's where you always start. This particular example, my initial energy will be 0 because the desk started at rest. It's not moving. So the initial is going to be 0. So 0 plus net work equals the final will be kinetic. And so my equation just ends up being net work equals final kinetic energy.
What time is it?
Okay, you have a computer in front of you. 0 plus net work equals final kinetic energy. Again, we don't have the kinetic energy, but we do have an equation for kinetic energy, 1/2 mv squared. So we can say that net work equals 1/2 mv squared. We're going to have to substitute in the equation for kinetic energy. And so when we do that and we plug in, it looks like this. You don't have to keep writing the 0 plus. You can just say work equals 1/2 times mass times final velocity squared. Again, because my initial velocity was 0, of course my change will be equal to the final, which is what we see here. And so when you multiply that out, 1/2 times 25 times 3.5 squared, you get 153.125 joules. That is the final kinetic energy, and so it's also the work that has been done because it's the change in kinetic energy as well.
Quick question. Do I write down dissipated energy?
Yes. All right, so again, we have work of positive 153.125 joules. All right, questions about that one? Okay, let's try another one. This one says a 0.65 kilogram ball rolls with a velocity of positive 4.1 meters per second when it rolls over a 2.8 meter rough surface with a frictional force of 1.15 newtons. What is the final velocity of the ball? Okay, so they've given us, again, some information here. Let's label it. We know the mass. We know the initial velocity is positive 4.1. We know that the distance that it's traveling in this question is 2.8 meters, and it is forward because it says it's moving forward. So this displacement will also be positive. If you want to write the positive sign in front of it, you can. However, my frictional force won't be positive. Remember, friction is always opposite the direction of the object's motion. So if it's moving with a positive velocity and it has a positive displacement, your friction needs to have a negative sign in front of it. Okay, so my friction is negative 1.15 newtons, and from that we're looking for final velocity. So again, I've got lots of information here. I have a mass, I have an initial velocity, I have delta x, I have f, and I'm looking for vf. Again, you can find vf in a handful of different ways. Okay, but we're going to start with our energy transfer equation and see if we can't use the energy equation to somehow find that. Again, energy transfer equation is the one where we are starting with our work energy theorem. Our initial energy in this case is kinetic, plus any work being done would equal our final energy, which is also kinetic, okay, because it's asking for the final velocity. Now, that final velocity could be 0 if it turns out that the ball stops, but it could be, it could still be moving. We don't know. That's the point of the problem. So we start out with some amount of kinetic energy. There's some work that makes it slow down, and we end up with a different amount of kinetic energy. Now, could you do this problem a different way? Probably. I see a force, I see a mass, I could find acceleration, I could go that way instead. Okay, you'd welcome to find acceleration and use kinematics. But energy is actually faster in most cases if you can write your equation. So again, I don't have kinetic energy given to me, so I need to use the kinetic energy equation in place of Ke. That means I need 1/2 mv squared for my initial velocity, plus my work, which will be my force of friction times my displacement. It's going to be a negative amount of work because my friction is going to cause it to slow down, equals my final kinetic energy, okay, which will be 1/2 mvf squared. So it looks like this. I know mass, I know VI, I know F, I know delta X, so I can substitute in. And the only thing I don't know is VF over here at the end, and that's the thing I'm trying to solve for. Now it doesn't really fit on my screen very well, so I had to kick it down to the next line, but this is my substitution step. 1/2 times 0.65 times 4.1 squared, that's going to be my initial kinetic energy, plus the work done, which is going to be force times displacement, with my force of friction being negative 1.15 times 2.8, and then my final kinetic energy, 1/2 times 0.65 times VF squared. Okay, so again, solve the pieces that you can. The whole left-hand side of the equation is equal to 2.24. So I went ahead and rewrote it. 2.24 equals 1/2 times 0.65 times VF squared. Okay, if you divide both sides by half of 0.65, you get this. And so now I have VF squared equals 6.9023. It keeps going. But I want VF, so I need to take the square root of that. And my final velocity is 2.63 meters per second. So the final velocity of the ball is 2.63 meters per second. And we were able to do it with a single equation. Again, could you do it another way? Sure. You have F, you have M, find A, and then use kinematics. But that takes a couple steps. Energy is faster once you get the hang of it. Okay, you can always check your work by solving it a different way if you have time. All right, so again, you should expect it to slow down because it says it had experienced friction. So make sure your answer makes sense. My initial velocity was 4.1. My final is slower. It makes sense. Okay, but double check it, because if you had something bigger, it means you probably forgot the negative sign on your friction. Okay, so you can catch those mistakes if you just make sure your answer makes sense. All right, how much energy is dissipated? Okay, so we know that we lost energy here. We know that friction did work, and we know that work is going to be responsible for the energy loss, the change in the energy. So we can use it to solve for the dissipated energy. Again, dissipated energy by definition is the energy that we lost due to the negative work. So if we can figure out how much work was done, that's going to tell us how much dissipated energy we had. Okay, again, you can go back to the same energy equation. Initial energy plus work equals final energy, which would be kinetic energy. Initial plus work equals final kinetic energy. Again, we've already written this equation a couple times. There's a shorter way to do this since we've already done this part, but we're just looking for the work there. Okay, so we know the initial kinetic energy right here. We know the final over here, and of course we can solve for the work from there. The initial kinetic energy is 5.463 plus work equals 2.248. So if I want to solve for work, I'm just going to have to subtract 5.463 from both sides, and I do get negative work. I should. Again, we already know there's energy loss. Okay, so the work done is negative 3.22 joules, which means the energy dissipated, the amount of energy that we lost is 3.22 joules. Okay, we wouldn't report it with the negative sign in front of it if we're answering how much energy is dissipated. We would just give an amount, the magnitude. But it would be 3.22 joules. It's equal to the work. And maybe you did that a different way. You could have just went back here and said force times displacement. It's the same thing. Okay, so again, you've got options for how to solve for that. But if you always start with your energy transfer equation, it's fail-proof. All right, questions about that one? All right, again, we already said that work is change in energy, and thus 3.22 joules of energy is dissipated.
So we write
All right.
this down?
Yes, you're writing it down. Okay. So again, you could have also done it this way. Dissipated energy is work. Work is force times displacement. And you could solve it this. It's the same thing. Shorter, actually, had you done it this way. Negative 1.15 times 2.8. Again, same exact number. Negative 3.22 joules, which again, if I asked you for dissipated energy, I just want the magnitude, 3.22 joules. All right, guys, that's it for today's notes. For the rest of the period, you now have time to practice what we just did. In the assignment 502.3 work energy theorem problem set, it is due tonight by 11:59 p.m. So I'm going to encourage you to get as much of it done in the room as you can. That way you have the opportunity to work on it with a neighbor, work through it, and ask for help if you need it. If you finish it in class, you don't have any homework. If you don't, you have homework tonight. The other thing that you have due is your RA, but it's not due till tomorrow. Now, I will warn you, you have another assignment tomorrow as well. So hopefully you finished your RA already. If so, awesome. If not, then you're going to have to keep working on that, but it's not There's not specific class time. Could you use time right now? Sure. If you do that, then you're going to have to work on this at home. Pick one. Okay, give me a minute. Okay, please note that the YouTube playlist now contains video solutions for 502.1 and 502.2 from earlier. So if you had trouble with any of those and you need to look at any specific problems, you can go back and do that. All right, guys, go ahead and get to work. Take out some paper if you don't already have it out. You're working on 502.3, and again, or you could be working on your RA, up to you. But whichever one you're not doing in the room, just keep in mind you'll have to do it at home.